Hello everyone. Thank you for coming to this session. In this session, Terashima and Futamata, engineers from the voice team of LINE Corporation, will present the development and operation of expressive speech synthesis system. First, we will give an overview of the speech synthesis and emotional speech synthesis technologies we are working on. Then we will talk about model development in emotional speech synthesis and the operation of speech synthesis systems, one topic for each. First of all, what is TTS? TTS stands for text-to-speech and means text-to-speech synthesis. It refers to a technology that generates speech from text. As shown in the slide, when text information is given, it outputs a speech waveform that reads it out. Recently, we seem to have more and more opportunities to hear synthetic speech generated by TTS everywhere. You probably hear synthetic speech in your daily life, such as in smart speakers and narrations at train stations. What you think is a human voice may be a synthetic speech. That is how rapidly speech synthesis has developed recently in terms of quality. The following section describes the technology used to construct the TTS. This section illustrates a type of TTS that consists of three major modules. The first is a text processing module. This module adds phonetic readings and pitch accents to the input text. The second is an acoustic model. It converts phoneme and accent information into speech features. Final model is the vocoder. It generates speech waveforms from speech features. Those are rough descriptions of the technologies that make up TTS. With the development of deep learning, the quality of synthetic speech has reached a level where it is almost indistinguishable from human speech for a relatively flat reading style. On the other hand, for speech styles that require expression and acting, speech synthesis technology has not yet reached the level of human skill, and there are still issues of expressiveness and controllability in current technology. The images you have in synthetic speech are also flat and lack emotion, I suppose. How are we going to tackle this issue? Next, I would like to introduce Coharis, a text-to-speech system we are working on. In order to realize and create voice services that require a high level of expressiveness, LINE is working on the development of a speech synthesis system that is as expressive as a human. The code name for this system is Coharis. Coharis aims to combine high expressiveness with a high degree of controllability to enable speech synthesis in a variety of speech styles in accordance with user requirements. So what exactly is Coharis? Based on the TTS configuration technology described earlier, the acoustic model is different. Coharis allows for a variety of speech and emotional styles to be selected for rich expressiveness. As shown in the slide, the system allows for expressive speech synthesis by specifying a range of styles, from the relatively flat neutral style to conversation, narration, and even emotional styles such as joy, sadness, and anger. In addition, for emotional styles such as joy, sadness, and anger, the intensity can also be specified, providing a high degree of control. We also plan to add even more style variations in the future. On the technical side, we are particularly focused on the development of emotional expression. So, what are the use cases for Coharis? Let's take a look at three of them. Firstly, audiobooks. In recent years, there has been a growing need for audiobooks which allow people to easily listen to books. Currently, voice recordings of voice actors and actors are the norm. But by using synthetic speech, it is possible to increase content without the need for new recordings. With Coharis's rich expressiveness, we can expect to achieve synthetic speech that matches a variety of genres, scenarios, and situations. Next case is automated phone answering. A flat response to a phone call with speech synthesis may seem tedious or stressful. With Coharis, it may be possible to give users a sense of intimacy as if they were talking to a person. Finally, narration. Whether it is a tense narration that calls attention to a situation or a friendly narration that conveys fun information, Coharis, with its high degree of control, can help you get your message across more easily. The speech synthesis system Coharis is composed of various technologies. Therefore, there are many technical topics in our work, but the following section will focus on one aspect of model development in emotional speech synthesis. It is a technology that builds an emotional speech synthesis model based on a small amount of neutral speech. This is based on a method adopted at the top speech processing conference INTERSPEECH 2020, and the following presentation is based on what I talked there. In order to build a TTS model with emotional expressions, there are several challenges in creating a database. First of all, of course, the emotional speech recordings data is essential. Emotional speech must be recorded for each speaker. However, there may be scenarios in which only neutral data with relatively flat readings can be prepared. There are many situations where there is a large amount of neutral data but no emotional data. In addition, recording emotional speech requires acting ability, which is a heavy burden on the speaker, and not everybody can do it well. How can this challenge be alleviated? We envisioned a situation similar to the one shown here. Suppose we have a speaker A with emotional data and a speaker B with only neutral data. Naturally, it is possible to construct an emotional TTS model for speaker A. How can we construct an emotional TTS model for speaker B who has only neutral data? One method is emotion transfer. By transferring the emotional expression of speaker A to speaker B, pseudo-emotional data of speaker B can be generated. As a result, the emotional TTS model can be constructed even though the emotional data for speaker B does not exist originally. We will refer to speaker A as the source speaker and speaker B as the target speaker. In our TTS modeling with emotion transfer, we use two techniques to augment the training data. One is voice conversion, which transforms the speaker's feature. The other is pitch shift, which transforms the pitch of the voice. Now, I will explain each of these steps in detail. Voice conversion is a technique for converting speaker feature while maintaining speech content. Voice conversion is also called VC for short. Here, we will train a VC model on neutral data for the target and the source speaker. Please listen to the speech samples of the target and the source speaker.
確認し
Let
ま
me
す
check
ね。
it.
よろしくお
Thank you.
願いいたします。
VC models trained by such data can be used to generate pseudo data for the target speaker from the source speaker's data. The next step is to generate pseudo-emotional data for the target speaker from the source speaker's emotional data using the trained VC model. Now please listen to the samples of the pseudo-emotional data generated.
よろしくお願いいたします。調子が上
Maybe
がっ
it's
てきた
getting
かも。
better.
それは
That
恥ず
is
かしいですね。
embarrassing. Thus, we were able to generate pseudo-emotional data in the target speaker who had only neutral data. There's one thing to keep it in mind here. Since the emotional data is more expressive than the neutral data, the dynamics of the sound height is also greater. Therefore, when training a VC model using only neutral data, variations in sound heights are important. We therefore augment our data with pitch shift. Pitch shift is a technique that converts the pitch of the sound while maintaining the content of speech. Pitch shift allows pseudo-generation of data with various pitch variations. Listen to the audio samples of the original pitched down and pitched up versions.
確認しま
Let
す
me
ね。
check it.
確
Let
認
me
しま
check
すね
it.。
確認しま
Let
す
me
ね。
check it. We intend to improve robustness and the quality of pseudo-emotional data generated by using these pitch shift data augmentation for training the VC model. Let me now describe our experiments. This time, we compared 3 different systems. The first is MSTTS, a multi-speaker TTS model. Here, we build a TTS model with 2 speakers. There is no emotional data for the target speaker, but we expect implicit emotion transfer from the source speaker. The second is VC-TTS, a TTS model using data augmentation by VC. The TTS model is constructed using pseudo-emotional data generated by VC. The third is VC-TTS-PS, a TTS model using pitch shift and data augmentation with VC. The difference from the second VC-TTS is that it uses pitch shift data augmentation when training VC. In this experiment, the first 2 are baseline and the third is our proposed method. First, a subjective evaluation of the naturalness of the synthetic speech was made by 14 evaluators on a 5-point scale. This is the evaluation of whether the quality is good or not. Against the baseline, our method was highly neutralistic and showed a marked improvement, especially in the happiness style. Please listen to the samples of the speech synthesis. Happiness style samples are played from the left system to right.
絶
An
品ミャ
in-depth
ンマーカレー
introduction
の
to
魅
the
力も
charms
徹
of the
底紹介。
exquisite Myanmar curry.
絶
An
品ミャン
in-depth
マーカレーの
introduction to
魅
the
力も
charms
徹
of the
底紹介。
exquisite Myanmar curry. An
絶
in-depth
品ミャンマー
introduction
カレー
to
の
the
魅力
charms
も
of
徹
the
底紹介。
exquisite Myanmar curry. Then let me play the sadness style samples from left to right.
拝見したいのですが、私には難しいようです。拝見したいのですが、私には難しいようです。拝見したいのですが、私には難しいようです。
Next, a subjective evaluation of emotional similarity was conducted with 12 judges in 4 levels. This evaluates whether the speech synthesis is able to reproduce the emotional expression of original speech. Similar to the naturalness evaluation, our method showed a significant improvement in similarity against the baseline, especially in the happiness style. The happiness style is more expressive of emotion and has greater pitch dynamics, so we think the pitch shift data augmentation was more effective. Finally, we conducted an experiment in which we reduced the amount of recorded data of the target speaker used for training in the proposed method to less than half. Specifically, the amount of recorded data for the target speaker was reduced from approximately 3.5 hours to 1.4 hours, but the performance both in naturalness and emotional similarity was not significantly inferior, even when the amount of recorded data used for training is reduced. One method was proven to be effective in smaller data volume situations as well. Let me summarize this section. We proposed a technology for transferring emotional styles using pitch shift and data augmentation with voice control. Our method was able to improve the performance of the emotional TTS model in scenarios where there is no emotional data for the target speaker. We found it to be particularly effective in the happiness style, a style that is emotionally expressive and dynamic. Audio samples and papers are available on the QR code page. More detailed information is available if you are interested. With this, I will hand over to Mr. Futamata, an engineer who is mainly responsible for the operation of the TTS system. I will now pass my microphone to Mr. Futamata.
Futamata from the voice team will talk about TTS system for product. As introduced in the previous part, LINE is developing a real-time voice synthesis system, Coharis. As Coharis has matured, the system has been redesigned and has transitioned from a monolithic structure to a microservices architecture. In this part, I will introduce our speech synthesis system, Coharis, and explain why we have redesigned the architecture. I will also introduce methods to speed up the inference, which is an important factor for real-time speech synthesis. This diagram shows the system flow for the internal modules using Coharis and an overview of the previously used monolithic system. I will describe the specific flow of system calls and an overview of the respective modules. The first step is to send acoustic parameters such as text, speaker, pitch to the system. The system then uses text segmentation and text normalization to split compound sentences into shorter sentences and normalizes the strings so that subsequent processing is more predictable. For example, the string 10 a.m. in the input sentence is normalized to 午前10時 or 10 in the morning. The G2P grapheme to phoneme module is then used to predict how the normalized text is read out. The G2P module is responsible for converting the written text into a series representing reading kana. For example, it converts the written text 10 a.m. in kanji into 午前10時 in katakana. Next, the phrase break prediction module predicts where a break should be inserted phonetically. For example, if the sentence あのね、あそこにね is entered, the module predicts where it would be easier to hear if a break were inserted phonetically, e.g., あのね、あそこにね. The accent prediction module then predicts the accent of the input sentence. As the Japanese accent is expressed as a pitch difference for each mora, this module predicts the pitch difference for each mora, i.e. for each character. For example, if the word onse or voice is included in the text, the accent is predicted to be higher on the o so that it becomes onse instead of onse. The results of text normalization, G2P, phrase break prediction, and accent prediction are then combined to create linguistic features. The linguistic features created here are used as the input series for the subsequent acoustic model. Acoustic models convert linguistic features into acoustic features, such as Mel spectrograms, which represent speech features. Okay? I see. Yes. Doesn't it change? I see. Okay. Mm-hmm. Okay, I see. Okay, I see. Okay, does it look okay? Okay. Okay, Futamata will explain about TTS system for product. As mentioned in the previous part, Line is developing a real-time voice synthesis system, Coharis. As Coharis has matured, the system has been redesigned and has transitioned from a monolithic structure to a microservices architecture. In this part, I will introduce our speech synthesis system, Coharis, and explain why we have redesigned the architecture. I will also introduce methods to speed up the inference, which is an important factor for real-time TTS. This diagram shows the system flow of the internal modules used in Coharis and an overview of the previously used monolithic system. I will describe the specific flow of system calls and an overview of the respective modules. The first step is to send acoustic parameters such as text, speaker, pitch, etc. to the system. The system then uses text segmentation and text normalization to split compound sentences into shorter sentences and normalizes the strings so that subsequent processing is more predictable. For example, the string 10 p.m. in an input sentence is normalized to 午前10時 or 10 in the morning. The G2P, grapheme to phoneme module is then used to predict how the normalized text is read out. The G2P module is responsible for converting the written text into a series representing reading kana. For example, it converts the written text 10 a.m. to kanji into 午前10時 in katakana. Next, the phrase break prediction module predicts where a break should be inserted phonetically. For example, if the sentence あのね、あそこにね is entered, the module predicts where it would be easier to hear if a break were inserted phonetically. For example, あのね、あそこにね. The accent prediction module then predicts the accent of the input sentence. As the Japanese accent is expressed as a pitch difference for each mora, this module predicts the pitch difference for each mora, i.e. for each character. For example, if the word 音声 voice is included in the text, the accent is predicted to be higher on the o so that it becomes 音声 instead of 音声. The results of text normalization, G2P, phrase break prediction, and accent prediction are then combined to create linguistic features. The linguistic features created here are used as the input series for the subsequent acoustic model. Acoustic models convert linguistic features into acoustic features such as Mel spectrograms, which represent speech features. Finally, speech is generated from the acoustic features and the synthesis results are returned to the user as a response. This is the basic system flow of the speech synthesis system and Coharis. Coharis consists of various modules. At the beginning of the development process, the number of members were small, and in order to increase the development speed, all the modules were combined into a large monolithic structure. However, as the product matured, 3 problems emerged with the monolithic configuration. The first is that each module is tightly coupled. As the number of Coharis developers increased, different members were responsible for each module, and changes in one module had an impact on the others. For example, there may be inconsistencies in the version of dependent libraries such as PyTorch, or a lot of effort was required to update some modules. In addition, the required input-output formats of APIs have become more diverse, which can bloat the system itself and make it more difficult to isolate failures when they occur. The second is development speed. Coharis relies on a number of in-house modules and their associated dictionary files, which increases the time taken to test and build before deploying. Third is scalability. In Coharis, some modules use GPUs for inference processing, but in some use cases, only some modules are used, so the GPU utilization rate of each module varies greatly. In this situation, the monolithic configuration requires each module to be scaled up equally, which leads to wasted resources. Like this, the limits of monolithic configuration were becoming apparent. This is why we considered the adoption of a microservice architecture in Coharis. There are 3 main reasons for adopting microservices architecture in Coharis. First of all, from the perspective of scalability. As explained earlier, the number of GPUs is limited, and horizontal scaling in a monolithic configuration was becoming unbearable. By making each ML module a microservice, it was possible to scale only the modules with a high load, which was expected to make efficient use of GPUs. Secondly, the number of application-specific use cases has increased. In some cases, tasks such as creating API handlers were also performed by ML engineers. With limited number of members, it would be ideal if ML engineers could focus on ML model development rather than server-side and infrastructure development. Finally, there was a perspective of development efficiency. Microservices were expected to reduce dependencies between modules, which will reduce build time. In addition, as individual modules can be deployed by testing and building only, dependencies on other members are reduced and development speed can be expected to increase. I will explain these 3 advantages in detail using concrete examples. Coharis, with a microservices architecture, has a flow similar to the diagram shown in the table. From right to left, it shows the microservices of each ML module, the proxy service that sends inference requests to each service and aggregates the results, the application-specific services, and the clients that use the application-specific services. Unlike the monolithic structure, each service in the backend microservice is provided as an independent API. The proxy service controls which microservice the request is sent to and processes the results. The first is from the scalability point of view. As each backend service is deployed as an independent service, services with high GPU usage, services with high memory usage can be scaled up individually. For example, the TTS services shown in the diagram, such as phrase break prediction, accent prediction services, and vocoder, make use of GPUs. Unlike previous configurations, these services can be scaled up horizontally independently, depending on the load on each service. Next, the increase in application-specific use cases. The assumption is that the proxy service is responsible for compiling the inference results of each ML service, processing the data, and returning the results to the application-specific services. The data processed and aggregated by the proxy service is used by the respective application service. As these application services have different inputs and outputs to and from the proxy service, they may use some of the back-end microservices and thus use very different amounts of resources. For example, Clover-related services send requests to generate speech waveform from text, so all modules such as G2P, phrase break prediction, and vocoder are used as back-end services. In the audiobook service, on the other hand, requests are sent to generate linguistic features from the text, so some modules such as text segmentation, text normalization, and accent prediction are called as back-end services. In other cases, a request is sent to generate speech from linguistic features. In this case, only acoustic models and vocoders are used. As there are a number of API-specific use cases as described above, the proxy service specializes in processing the application-specific API handler and in aggregating and processing the results of the backend microservice. By separating the proxy service and the backend microservice in this way, ML engineers no longer need to deal with application-specific use cases and can concentrate on developing ML modules. Next is about speeding up the development process. Each backend microservice is provided as an independent API, as mentioned earlier. Therefore, compared to a monolithic configuration, the testing and build time for each service is reduced, and it is easier to work in parallel and independently.
I will also introduce efforts made to speed up inference speed when revamping the application. First, let me talk about CPU-based speech synthesis workers. Because of the limited number of GPUs currently in operation at Coharis, it is not possible to prepare for a rapid increase in requests by utilizing autoscale. Therefore, we're using multiple parallelization of low-speed CPU-based TTS to cope with the rapid request increase. In addition, a dynamic server batching method called adaptive batching is used to speed up the process. This allows efficient use of GPUs by dynamically batching requests from different clients sent at short intervals, such as several hundred milliseconds, and sending the request to each backend service. In addition, gRPC is used for communication with each backend microservice and proxy service. gRPC was adopted instead of REST to reduce communication speed as much as possible since real-time performance is required for Coharis. Considering the above advantage and speed-up techniques, here is the structure of the newly created Coharis. First, I will explain the flow of API calls. As explained earlier, the Coharis server calls proxy service from application-specific services. The proxy service then calls backend service via gRPC based on the caller's API. If there is no need to generate arbitrary speech in real time on the application side, a CPU-based speech synthesis system can be used. In a CPU-based speech synthesis system, a speech synthesis request is sent as a job to a Redis-based pub/sub via proxy service. Jobs registered in Redis are inferred using CPU-based acoustic models and vocoders. CPU-based workers can easily scale horizontally compared to GPUs, which are limited in number. By multiplexing and parallelizing low-cost, low-speed CPU-based TTS in this way, it is possible to respond to a sudden increase in the number of requests, for example. In addition, cache storage is invoked by proxy services, model storage by backend services, respectively. Cache storage contributes to accelerate synthesis by caching the synthetic speech into S3-compatible storage. The model storage is used to store and load ML models used by each backend service. Since acoustic and vocoder models are frequently updated, external loading of models contributes to reducing build time and pod startup time. In addition, each backend service uses ML model serving tools such as Triton and TorchServe. These serving tools enable monitoring, metrics, logs, and creating REST APIs and gRPC APIs for inferring models by simply wrapping the inferred model. As a result, ML engineers can focus only on the core of the ML model. Finally, I will discuss the advantages and disadvantages of the architectural change. The first advantage is the development of efficiency has improved. By subdividing each module as a microservice, ML engineers can focus on model development. Also, in terms of scalability, GPUs can now be used efficiently. One disadvantage is the complexity of the procedure to release. Since the proxy service is responsible for binding each module and each backend service is used in tandem, if the input-output sub-modules is changed, all modules will not function, so the release procedures must be kept in order. Second, it is difficult to prepare a local environment. Previously, Coharis was managed by monitoring single repository, but currently it runs on environment with Kubernetes, which makes it time-consuming to build a local environment. This is a summary of this part. I introduced our TTS system we developed, Coharis. By adopting a microservice architecture, ML engineers can focus on ML modules only, taking advantage of their expertise. In addition, the separation of each module has reduced dependencies on other modules and greatly increased development speed. This concludes my presentation.
発表は以上
That's
とな
all
ります。
for our presentation.
ご視聴いただき
Thank you for
あ
watching.
りがとうございました。
Thank you. Mr. Terashima and Mr. Futamata, thank you very much. From this point on, with the title of Plus Talk, we'll go deeper into the contents of the session based on the interest of the questioner. Mr. Junpei Miyake from Yahoo Japan is an interviewer. So, Mr. Miyake, please briefly introduce yourself. Thank you. I'm a manager of Speech Recognition Technology, Science Division at Yahoo Japan. Pleased to meet you. Pleased to meet you. Thank you. Now, Mr. Miyake, what points were you interested in after listening to the session? Well, first of all, my impression after listening to the presentation is that it is a highly expressive speech synthesizer, and I was surprised with its speech quality, even though there is a lot of intonation. I have not heard much about system design for speech synthesis production before personally, so I thought it was a very valuable talk. Thank you very much. So let me ask you firstly, about the pitch shift data augmentation. I'm just trying to match my understanding of the concept. The emotional speech has a very wide range of pitch, and DC is learning from neutral speech. And for example, very high-pitched speech is not available in neutral speech. Therefore, you are motivated to improve the training data or to improve the coverage. Is that right? Yes, that is exactly right. To use a very simple example, the happiness style used in this experiment is a joyful speech, so the pitch is often much higher than that of a neutral speech. Since such data is not available in the neutral data, pitch shift is used to support the high-pitch data. I see. Thank you very much. Yes, that's right. I think it is important to improve the performance of the VC model as an approach, but it is also important to improve the quality of the data to properly learn through data augmentation. Thank you. As for VC, you mentioned that the data is augmented by pitch, but how many times is the data actually extended? In this experiment, as illustrated here, the data is about 15 times larger due to data augmentation, since it is from -3 semitones to +12 semitones. Maybe you might be wondering why this range is set in this way. It is based on a preliminary experiment so that it is sufficient for the emotional data used in this study. However, we have made it a little wider so that we can accommodate a wider range of requests. Then, let me explain why the number was set at -3 and +12. The pitch shift technique we are using now is not very good at lowering the pitch, so I have to narrow the lower range and expand upper range since it is good at raising the pitch. I see. Thank you very much. So, maybe you decided looking at histogram or width of the pitches and others. Right. I haven't looked at the histogram level, but we have tried to cover almost all the range. As for the range between -3 and +12, the data is uniformly converted by the unit of semitones, -2, -1, +1, +2, and so on. Thank you very much. I think you also mentioned that you're planning to increase the number of speech styles. But do you have any other effective ways to augment data in mind? If you're considering some, may I ask what they are? Well, this is not about data augmentation, but in this experiment, there are 2 speakers, one only with neutral data and one with emotional data. And if there are several other speakers who have some kind of emotional data, we can mix them all together and use them for training. In this VC, it is a 1-to-1 conversion model, but I think it could be made into many-to-many model with multiple speakers. This would allow us to increase the quality of voice conversion and the degree of support without pitch shift data augmentation, since we think a variety of pitches can exist among different speakers. Thank you. Yes, I think you mentioned various speech synthesis system configuration like voice conversion and acoustics as well as vocoder. If you could tell us what kind of methods you use, then that would be great. Yes, Coharis has a different methodology depending on the versions, so let me explain based on the materials used in this experiment. Fast Speech 2 is used for acoustic model. As for the vocoder, we are using a method called HNPWG created by Ryuichi Yamamoto, a member of our voice team. VC is not included in this figure, but we are using a model called Cyclone for VC. Thank you very much. Since you mentioned that this is what you presented in your INTERSPEECH, I would like to read some details on what. Thank you.
Another thing I wanted to ask is when training the acoustic model in TTS, I'm not sure if Fast Speech 2 applies, but I think in many cases you acquire the speech through automatic alignment. I understand automatic alignment is difficult for emotional speech. How did you go about that? In the Coharis experiment, we did annotation by hand. For alignment of phonemes and accent information, the annotation was done manually. That's why the quality of annotation is high, and that is directly linked to the high quality of TTS. Having said that, research is ongoing to make it possible to train TTS even without alignment. We also wish to incorporate that going forward. It's nice that all the alignment was done by hand. That's right. Have you compared the quality between automatic and manual alignment? Is there a significant difference in quality? I have not looked into that in detail. That comparison may have been done, but I'm not aware of the details. Okay, understood. Thank you very much. About the acoustic model, did you develop discrete acoustic models for each emotion, or did you give emotional labels like one hot vector as part of the feature? How were emotional TTS models used? Currently, we use emotional labels. We do not develop models separately for each emotion, but one model covers multiple emotions. In case of Coharis, 3 labels, speaker label, emotion label, and emotional intensity are used for training. One single model handles multiple speakers, speech styles, and emotional intensities. I see. Will the quality be different when you use one single model or have different models for each emotion? Maybe there might be cases where the quality is better if you use one model. However, we have never done a strict comparison. We are now handling multiple emotions and speech styles using 17 speakers, and the quality is very high. So even if only one model is used, I believe it is possible to realize high quality. Thank you. I was surprised to hear that you were using 17 speakers. And using one model would make operation easier, so you're right, that might be better. Thank you, I understood very well. I would also like to touch on the system side. In the slides, you mentioned phrase break. Acoustic model and vocoder use GPU. Right. You also said that there's a limit in the number of available GPUs. Generally speaking, having a large number of GPUs in production, I believe, would have cost challenges. That is the general impression. Considering the scenarios in which Coharis is used, what will be the upper limit of the number of requests or QPS? Please move to page 41 in the slide deck. First of all, as you just said, phrase, break, accent, and TTS are the modules that use GPU. On the definition of QPS, in case of line, we have been offering Clover Voice service. In Clover Voice, 20 requests per second is used internally. Since Coharis is also meant for internal use, we defined the criteria based on this number. The criteria for real-time TTS, on the other hand, is 0.2 RTF. This means 1 second of speech should be generated within 0.2 seconds. We also made use of this criteria, which already existed. Compared to voice recognition, TTS is not that GPU intensive. Currently in the production environment, 4 NVIDIA V100-132G are used. With this, we realize 0.15 RTF with 30 requests per second. Thank you. By the way, I think each service has become microservice, with each module being loosely coupled. I believe there will be communications through APIs. Wouldn't that be a bottleneck? Although we have not looked into the details on the latency of API communication, as I explained earlier, we have realized about 0.15 RTF for 30 requests per second, so we see no problems as far as real-timeness is concerned. So we don't see any problems here. Thank you. Another point I wanted to ask was CI. I was wondering how you perform integration tests. Every time there's a change to a module, you will perform unit tests. But considering the end-to-end process, starting from language analysis to forming the voice waveforms, I think it is also necessary to perform integration tests to see if everything is in alignment. After make any changes to a module, what does the flow up to the integration test look like? Currently, we don't have automated integration test. We are now operating on Kubernetes, and on top of the Kubernetes cluster, there's a CPU-based personal environment for each developer. When a developer commits a change on GitHub, that will be automatically deployed on the personal environment of each developer. If a module is partially changed, you can test the impact on all the modules. Each developer will do their own test in their respective environments, and if there's no issue, they deploy to either the test environment or production environment. Is the change automatically deployed to the personal environment? Yes. It is classified based on branch prefixes. For example, there are prefixes such as dev1 and dev2. If a change is committed to that, it will automatically be deployed. I get it, thank you. If there is a substantial change, which also depends on other components, and if you want to move to the new architecture without stopping the service, how can you make the shift? Do you control this using versions? Right, basically, ML modules do not depend on any other ML module. That is how the system is built, so we believe that situation will not occur, but each ML module depends on proxy modules. So, for example, if the phrase break module input or output changes, the input or output of the proxy service needs to be changed accordingly. We do versioning so that the versions of the ML module and the proxy service module are in alignment. That is being done. I see, you can do the control from the proxy service side, so it will be fine. That's right. Thank you. We are approaching time, so I will make this my last question. I see you have been going through various trials and errors on models and systems to realize a highly accurate system. What were the difficulties you faced and how did you overcome them? Okay, starting with me. I'd like to share the challenges we faced and how we overcame them. In this experiment, we were mainly developing the VC part. The cyclone model we used this time for VC. In the original academic paper, they were trying this out with female speakers with 5,000 sentences. In our case, we used a much smaller data sample, and we also wanted to incorporate male speakers. That's why we had to make the acoustic features male spectrogram, which is more efficient, and we also changed the bar width. The VC is cycle GAM based. It worked better when we had smaller models and kernel size for the generator and disk emulator, so we made that adjustment. And although this is not included in this report, having a spectral normalization layer in the generator realized higher stability. We incorporated such small detailed changes to improve the BC. Tamata-san, anything from your side? From the system side, Coharis was originally built as a monolithic configuration, and it was very tightly coupled. From that state, we wanted to shift to a more loosely coupled state. Dismantling the system was a little bit challenging. There's also a challenge we are facing at the moment. To G2P and text normalization models, dictionary files are added from time to time. We currently do not have a system to efficiently add these dictionary files. That's why updates to modules themselves happen quite frequently. That is the challenge we are facing right now. That was all from me. Thank you. It was very interesting to hear also about things that were not on the slides. Those were all the questions I had. Thank you very much. Thank you.